Hi there. In this video we're going to be looking at random networks such as that one on the top left here, and we see how we could possibly turn that into a Thevenin or indeed a Norton equivalent circuit. And ultimately what we'd like to do after we've discussed some theory is to be able to predict which sort of load resistance is going to achieve maximum power transfer from left to right. Okay, so let's begin our analysis. Okay, so we're going to be looking at Thevenin and Norton equivalent circuits. Before we do so, of course, we're going to need to draw another type of circuit, which is just a basic DC network. So let me see if I can get some black ink and start off with a battery. A resistor I might call R1. Another one I'll call R2. I'm going to have two terminal arrangements here, A and B, and I'm also going to have R3. Okay, and maybe I can call this the supply voltage S. Okay, but it's basically the battery, it's DC. What I'd like to be able to do is to think, well, you know, that could be a much more complicated network. It could have, say, 15 resistors in there, all in series, in parallel, wherever it might be, which is not too nice to analyze. Wouldn't it be useful if it could have an arrangement that looks a bit like some equivalents? How about a single battery, a resistor, and that's it? Okay, so A and B. What is this sort of arrangement known as? It's known as a Thevenin equivalent circuit. Okay, a Thevenin equivalent circuit. And this resistor, therefore, is known as RTH, Thevenin resistance, and predictably this one's known as VTH, the Thevenin voltage. We'll describe shortly how we arrive at these values, okay, for these particular devices, components here. Another type of equivalent we could have is a Norton arrangement. Okay, again we could have A and B there. Then we have a resistance in parallel with this current generator. As I said, it's a symbol for the current generator. You may also sometimes see an arrow pointing up there, depending on which software application you're using for simulation. Okay, so this is a Norton equivalent circuit, and predictably this is going to be R subscript N for Norton, and this is going to be I subscript N. What we'd like to do now is let's see if we can generate from this circuit on the top left here a Thevenin equivalent circuit. When we do so, it's very, very easy to then generate the Norton equivalent. Okay, so I always recommend to you that you try to work on the Thevenin circuit first. Okay, let's do a quick subheading here then. So Thevenin circuit, shorthand. Maybe I'd like to give these things some values. Why don't we, let me just change to red. Let's call this battery, say, 9 volts. R1, I'll make 3 kiloohms, 3K. I should write 3K omega really, but shorthand's okay when you're doing circuits like this. 4K, about 6K maybe. Right. What I want to be able to do is to say, what's the value of this VTH here, the battery, the Thevenin voltage? Well, the Thevenin voltage is the voltage you'd see across A and B when there's no load across A and B. Okay? If there's no load across A and B, then this R2 here is just sitting there, not doing very much in particular. So effectively, you've just got a series arrangement here. You've got this battery supplying R1 and R3, which are in series, back to the other end of the battery. So what we're going to then say is the Thevenin voltage is equivalent to the current in that loop there in red, and that's a bit of Ohm's law there. This is going to be 9 over 3k plus 6k. There's the current in brackets. We're going to multiply that by R3, which is a 6k. Okay, so that's looking a bit like 9 times 6k over 9k. Right, so what's cancelling here? Let's do some green. The 9 and the 9 cancel. The k and the k cancel. It's looking very much like 6 volts. And that's correct. So VTH is 6 volts. So a 6 volt battery. What about RTH here? This one, Thevenin resistance. How do we work that one out? Well, to do that, let's first of all write down what we're trying to achieve. To do that, what we're going to do is take away the battery completely and replace it with a short. Okay, or link. Then what we're going to do is, why don't we have a little look down from points A and B and work out what that resistance is that we see from points A and B. That will actually give you the Thevenin resistance, RTH. Okay, and what are you seeing there? Well, I'm seeing R2 in series with this combination here. Okay, so I'm seeing R2, which is 4K, in series with, hence the plus sign. R1 and R3 are in parallel. Okay, so it's going to be looking something like 3K times 6K. So product over sum, remember, for resistors in parallel. 3K times 6K over 3K plus 6K. We simplify this a little bit. 4K plus, okay, and in those large brackets, you're seeing 3,000 times 6,000 is going to give you 18 million, divided by obviously 9,000 on the bottom. Okay, so 18 over 9 gives you 2, 1 million over 1,000 gives you 1,000, 2,000, so 2K. Okay, so overall we're seeing RTH as 4K plus 2K, 6K, or 6 kilohms to be complete. Okay, so 6 kilohms is our Thevenin resistance. Okay, what about the Norton circuit? The Norton circuit and a subheading. Right, well, I did say earlier, you know, it's quite easy to work out the Norton circuit once you have the Thevenin circuit. And this is how you do it. You're going to say the Norton current is equal to the current that you might achieve if you went from A and B with an ammeter in your Thevenin circuit. So up here, A to B, if there was a short there, what would be the current in the Thevenin circuit? Okay, so mathematically it's going to be VTH over RTH, of course, once A and B is shorted in that Thevenin circuit. So that's going to be 6 volts over 6,000 ohms, okay, which is going to give you 1 milliamp. So just switching back to red, so this thing here is a 1 milliamp constant current generator. Okay, and what's the value of the Norton resistance? Well, it's actually the same as the Thevenin resistance. Easy enough, although in the Norton case, of course, it's in parallel rather than in series. Okay, and we work that out to be 6 kilohms. Okay, so that thing's 6 kilohms as well. Okay, so maybe what we'd also like to know is what's the ultimate value of load resistor? Let me just change to purple. What's the ultimate value of RL, the load resistor? Or I could stick on, pick the Thevenin circuit as a favourite. What's the best value of load resistor that goes there so that I can achieve maximum power transfer from the battery? Okay, and we'll be able to plot various types of load resistor in the microcap simulator. So that's what we're going to do next. We're going to have a look in the microcap simulator, and we're going to produce all of these analyses there. Okay, and I've set up that network that we analysed earlier. Here we have the 9-volt battery, 3K, 4K, 6K resistors, and below I've drawn the equivalent Thevenin circuit, okay, which we determined to have a 6-volt Thevenin battery and a 6K Thevenin resistance. Also, we have the constant current generator of 1 milliamp and the Norton parallel resistance of 6K, and we need separate names for these outputs here. So that A and B1, A and B2, A and B3, otherwise the simulator won't know which particular output you wish to simulate. You'll notice also I've drawn a load resistor in here, RL. In advance I know what this optimum value of RL needs to be in order to get maximum power transfer from the battery there. But let's see if we can get microcap to do all the hard work for us and tell us which value of RL is the best to choose. One thing you may not have done before is bring in a constant current generator. And to do that, you need to go into your analog primitives over on the left here. You go down to waveform sources, which is the third one down, and you're picking this particular item here, I source, I for current, so constant current source. Click on that, bring it into the circuit. If I left click and hold that left click and then right click once and then once again, I can change its orientation like so. Okay, but I don't need a second source in, so just going to cancel that one and just hit the pointer here to go back to normal analysis. Okay, so let me do some simulation on this circuit then, and let's see if we can produce the results that we want. We can click up here on analysis, and we're going for DC, that third one down there. Okay, DC analysis. You'll notice there's a dialog box which has popped up here. Okay, and you need the settings pretty much the way I've done them here. So we've got linear variable, the name for the variable that I'm going to simulate, to step its values from 0, which I've done here, all the way up to 24,000 ohms. Now you'll notice as I hover over this little box here, on the very bottom of the dialog box down here, it disappears, but keep your eye on this area down here as I hover over the range, and it tells you it sets the primary source sweep. Okay, so it's going to sweep from a final value, which I've got as 24,000, then a comma, then 0, which is going to be the initial value, or 0 if you like, and start at 0, and step RL up to 24,000, and we're going to do it in steps of 100 ohms. Okay, so 24,000, comma 0, comma 100. Okay, by default we leave the temperature at 27 and the number of points also. And what we can do with the X range and Y ranges, I can left click here and make sure I select auto always for the X range, and also for the Y range, left click on that heading and then click on auto always, which is pretty much what you want to do on most of your circuits. Okay, and next thing to do is hit run, and hey presto, we have a graph. Now what this graph is saying to us is we have RL along the horizontal axis, and it's going from 0 all the way up to 24k. Okay, so it's also giving you the power PD in RL up here on the vertical. And so the point where we have maximum power transfer is round about there. Okay. And we're getting a maximum when RL is around about 6K or so. That's what it's saying. It's quite difficult to do. You can have a zoom in, I suppose. Let me try zoom in on there. Then go up here some 5.9888, so very close to 6. Here we are, that point there. And that's the point of maximum power transfer. So we got around about 1.5 milliwatts of power transfer to RL at that point. Okay, so if I was just to kill that window for the moment and go back to this thing here. So in advance earlier I said to you, I know the value of RL, the optimum value. So I can double click on that. It was actually 6K predictably. So I can click on show for that and then OK. And then that 6K pops up in here. Okay, so overall then, if you want to achieve maximum power transfer from a circuit to a particular load, then you need to match the load to the source resistance. Okay, so in this case the source resistance is best viewed from the Thevenin equivalent circuit, so it's 6K. Okay, interestingly, we also thought, okay, maybe we could do that with the Norton circuit, so put a 6K load across there. If you've got a 1 milliamp current source supplying these two resistors, a 6K and then a further 6K between A3 and B3, then you're going to have half a milliamp flowing through each one, of course, okay, because there's symmetry there. So you can have half a milliamp flowing through a 6K load resistor. So power is I squared R, so 0.5 milliamps squared times the resistor value of 6. That is going to give you 1.5 milliwatts, which is what the graph said. Okay, so hopefully that's been helpful for you, and I'll see you in the next video.